Okay, tell me, Scott, tell me your name and what you're up to.
My name is Scott Draves, and I'm a software artist. And so I create abstract art, video, computer graphics by programming computers. My main project is called The Electric Sheep, and there's multiple versions, but there's the way that most people know it is as a screensaver. That's a free download, runs on any computer, and the way it works is everybody who downloads the software participates in creating the artwork that everybody sees. So, and it's really, my objective is to form a kind of an artificial life form, and the artwork is really about the relationship between man and machine, and our relationship with the world of information.
So how do you do that? What do you do to build that relationship?
Well, in this case, it's the way it works. The form of interaction. What people actually do is vote, and so and that drives a genetic algorithm. So each of these images, each of these animations that appears on the screen, is one sheep, and it has a genetic code, which is a whole bunch of numbers, thousands of numbers, which control how it looks and how it moves, the colors, the textures, and it's really the way it looks is it's made with a mathematical algorithm that I invented about 20 years ago. It's called the flame algorithm. It's really not like normal computer graphics. It's done with drawing lines and circles and dots and polygons and whatnot. It's a really different approach. The image is created by solving an equation with thousands of parameters and millions of variables. Essentially, every pixel is a variable, and so it takes the computer about an hour to render one frame of animation, and so that's why you need thousands of people running the software and all those computers working together as a supercomputer and sharing the results in order to create the art.
Why do you call it sheep?
Well, Electric Sheep comes from, it's a reference to an old book by Philip K. Dick, Do Androids Dream of Electric Sheep, which got turned into the movie Blade Runner, which was pretty popular. So, but I use that name not because the art is really about the book or the movie or what Dick was saying. It's not a thematic thing. It's simpler. The idea is really because when your computer goes to sleep, the screensaver comes on, and so it's the computer's dream. And so, like when people go to sleep, we count sheep. There's I don't know if it's a fairy tale or the children's drawing. So the idea is just to refer to the computer's dream, and not just your computer, but the computer, the internet-wide supercomputer.
So how many computers are dreaming of sheep right now, do you think?
We have 450,000 monthly uniques. So. And we're pretty much limited by by server capacity, and it's all the computers work together to create the art, and all the people, like I said, everybody who's watching is voting on whether or not they like what they see, and so we use the Roman justice system for the Roman interface. So it's thumbs up for life, thumbs down for death. The sheep that people don't like die and disappear. The ones that people do like mate with each other, they reproduce, they have children. So variation and selection, those are the ingredients of Darwinian evolution. So the artwork is evolving to satisfy human aesthetic, the collective aesthetic of the audience. And so, as time goes by, the things that people like, it does more like that.
Can you tell us more about how it evolves? What exactly is the DNA of the art, if you will?
Well, the DNA are all the parameters for this equation, and the equation is a recursive set equation. It's fundamentally something like an iterated function system, I would say, which is something that's been around in mathematics for probably 100 years originally, and then, but really, it's something like a combination of a particle system and a fractal. The idea is that you have a collection of transformations from the plane to the plane. So geometric transformations. And then the image is the resonance, the spatial resonance created between these spatial transformations. So
What makes it resonant? Is it the perception of what the users see, or do you detect that in your algorithm?
well, it's the resonance is detected by the particles. So you throw actually billions of the tiny little dots of light in, and they move according to the functions, and then wherever they end up most, which is where they're resonating, is where the shapes of the image appear. And so it's really, like I said, this is really sort of different from normal computer graphics, and different from normal art, where the traditional art is where the artist has a vision, an idea in their head, and they transmit it through their hand or through their brush. They put marks on the paper to create the image. And so this is really different, where me as the artist, I've given up control, and I'm using sort of randomness and my audience and open source. So really, that's which is a whole other part of the project, in order as part of the process to create this, to create this animation. And so there's some trade-offs involved in that. And so, everybody voting and to control what everybody sees. It sounds very democratic. It sounds like it's going to, everybody gets what they want. That sounds great, but there's a downside too. Like sort of popularity is not necessarily, and aesthetics is kind of a complicated mixture. So I call it the Las Vegas effect, where the sheep that get the most votes tend to be the flashy, trashy ones. Bright colors and fast motion is not, what I think is truly beautiful. And so, so this screensaver version is really a pop, sort of channel for this technique. And so, what I also do, and what I'm more known for in the art world as opposed to the sort of internet world, is taking all the things that the software does and editing it. So, this project started in 1999, the Electric Sheep, the internet version of it, and over the years we've collected thousands, literally hundreds of thousands of sheep. They're all archived online with their lineages, and so what I do is I go through all these things, pick out a few, the ones that really I think are beautiful, and then send them back out to the network and re-render them in high definition, so much higher quality, much slower motion, and then edit them, assemble them, and sort of create coherent collections that are limited edition fine art. And so that is sort of appropriate for the gallery, the museum, the corporate lobby, whatever. And so those objects have a really different feeling, although they're based on the same algorithm.
So does your art speciate? Do you get new species as you go? Is there just one species?
Well, any sort of technically any sheep can have sex with any other sheep. So it's
Okay.
and by that definition, there's only one species. But there are lines or styles. By the common notion of a species, of sort of some variation, but the sheep that look alike or have a certain structure. Certainly, yes. There are, the successful certain genes that are very cool and have done sort of amazing things, and those I call them lineages or families, um, and there's a number of these groups actually, or even, and I've created a series of Blu-ray. One, in order to deliver the art. Normally, I deliver it on computer so that it can do the sort of infinite playback. But I've created for people who don't want to deal with the hassle of the electronics. I've made Blu-ray discs which have fantastic video quality but are a static medium. A series of these called clade, which is a term where I take a collection of sheep all from the same family, all that share a common gene, that share a common visual style. So it's kind of like a theme and variations from the musical term. Anyway, and put them together. And so clade is a term from evolutionary biology that refers to one branch of the tree of life. As a collection of individuals that share a common ancestor.
Talking about the internals of how you do it, I understand it's a parameter-driven model, so your DNA is actually variables that you feed into the function that you've pre-programmed. I've been interested in L systems as a linguistic model of what you're doing, so you can build a language in tokens, and the iterative function model interprets the language. So it's actually a linguistic interpreter where you're doing a pre-programmed function with a varying set of parameters. And I guess I'm really fascinated by the linguistic level of actually evolving the language at the linguistic level rather than just parameters at the defined function level.
That's right. Well, and my PhD thesis was on languages and actually languages for creating languages. And
okay.
So
by the way, that was my career, is defining meta languages. I've never written an API in my life. I was always designing a language above the problem.
We have a whole other thing that we have to talk about.
Okay, great.
That's really interesting. But yeah, and really, this electric sheep thing sort of is in a sort of sideways way derived from those ideas or that research and that philosophy.
But it's basically a finite state grammar, if you will. You've defined the grammar and you're feeding it with different parameters.
Well, but it's and parameters, people think of it as like a couple of dials and you're only going to get things within a certain space. And I totally agree with you on sort of the difference of creating languages where there's sort of something that really emerges from it. And what's really remarkable about the flame algorithm is that it actually has that property of emergence, and it has a million different looks. And really the thing that distinguishes the electric sheep or the flame algorithm, that it's based on, from almost all other computer art, is that it's one program, but it doesn't have just one look. Because it is a language, it has many different styles, all derived from this one process.
How do you call it a language? Isn't it just a vector of genes?
Well, but it can be a long vector, and those genes interact with each other in mysterious ways. And so I call it a language because, well, for a couple reasons. One, to evoke or to refer to Kandinsky's notion of the visual language, which is the notion that you can sort of say things with images, and that images, even though they're not, Kandinsky was more or less the father of abstract art, a painter, and that was when art was really leaving the notion of drawing pictures of things, representation, which obviously you can say things by drawing a picture of that people recognize, a person, a place, an object. But Kandinsky's idea was that just the shapes themselves and the colors can evoke emotion or can express something. And so I'm referring to that these flame images or these sheep images communicate emotions and but also.
But that's the language of the produced product. The intermediate language, you don't have a meta language defining the the genes. It's a digital sequence or vector of floating point numbers that you feed it. So it's a purely syntactic internal process.
Well, the actual format is XML, so it's somewhat hierarchical.
Okay.
And then the meta language is just C, right? So which programs, the translation from the genetic code to the images is programmed in C. But it defines, but it does define a language where there's, I think there's a real emergence, there's a real semantic gap between, and this is what I mean by the difference between this and normal computer graphics. In normal computer graphics, the semantic, the XML file format might list the coordinates for some, the endpoints for a series of lines. And then the image, you draw those lines. Well, there's not really that much of a semantic gap between the coordinates for some lines and then the lines themselves.
Right.
It's sort of like a one-to-one mapping. But what's really different about the flame algorithm is because there's this equation solving thing, there's real emergence, there's there is a difference between you can look at the genetic code and look at the image, and the connection between them is surprising and mysterious and unpredictable. Just like you can't derive, you can look at the sounds of the sentence, the sun is sparkling on the river, and that doesn't really tell you, just those sounds doesn't tell you about the experience, the qualia of the sun sparkling on the river, which is what I see right over here. But so there's a semantic gap, right? And that's the experience is more than the sentence, and just the flame algorithm actually does have that property because it is it does feature, or it does produce emergence.
But it is constrained to the functions you've built into it. It's going to be bits in a plane, and it's not going to invent a three-dimensional space over two. You've constrained the dream to a two-dimensional plane.
It's true. But what's amazing about it is that it, and its essential property is that it does continue to, even after all this time, it continues to surprise me and do things that I didn't put into it or anticipate, and it does things that I don't understand. It blows my mind, the things that I see that sort of come out of it, that are evolving, and that's this sort of what I'm talking about. This essential property of the emergence, or the semantic.
Yeah,
gap.
In my Tom speak, I have my own language for these things. I call that crossing an organic threshold.
Yes.
And the parts now collect into a new way that
Yes.
the whole is different.
That's right.
So what is it that allowed that threshold to be crossed? And did you anticipate it before you built it?
Well, it wasn't really anticipated. I didn't, I never really set out to do this. So it's kind of accumulated over many years of experience and practice. But really, I think some of the essential ingredients was one of them is really supercomputer power. I think was really key. And that's part of the difference from normal computer graphics. Drawing those lines is really easy, but solving the equation is hard, and that's the work is required to make the leap.
Now, were you solving the equations, or were you plugging in the variables and evaluating it?
Well, you take the parameters, and then the variables are actually the pixel values.
Okay.
And the solution, you could formulate it as a matrix.
Yeah.
But in fact, we do and do sort of what you call a backwards solution. What I actually do though is a forward solution, just by throwing all the particles in and simulating their motion.
Yeah.
And statistically, they accumulate and come up with the solution.
So what do you think created the emergence? What was the key element of your design that allowed emergence to happen?
Well, it's the the nonlinearity, the randomness. I think because it's the particles. There's a random number generator that as you pick which function is applied to them is part of it. And then an important ingredient though that really sort of kicked it from, because like I said, the essential math had, of these iterated functions. So one of the ingredients was the supercomputer power. But another ingredient, and the one in particular that I added, was the visualization technique. So people have been sort of doing things like iterated function system for 100 years, strictly and mathematically, but they didn't have the particles. When you solve these equations, you end up with distributions that follow a power law. And so if you just draw the particles, which is what everybody had done, you sort of treat the image plane as a binary, either in or out. And that's what mathematicians had done for a long time. That's how they think. It's a recursive set equation. You're either in the set or you're not in the set. If you approach it that way, you end up with kind of crappy images, and it doesn't really do it. It doesn't have that organic feel. And so one of the things I did was find a technique for that really reveals the complexity of these sets by not treating them as binary things, but treating them as having not even just treating them as pixel values, like sort of integer, 8-bit red, green, blue kind of images, but because they follow this power law, treating them as floating point numbers with high dynamic range, and then using logarithms to reveal the whole image, and so that you could see. Normally, with monochrome it's even worse, but even with 8 bits, you just can't see everything. It's either a few little dots at the high points, or everything is washed out.
So how high is your range? How many bits or?
Well, it's floating point.
Floating point.
We use 32-bit.
Okay.
We use 32-bit floating point accumulators. And
Okay.
There's 4 of them per pixel.
Yeah.
And then and then it's super sampled, usually 4x4 per pixel. So that's 4 times 4 times 4. It's 64 floats per pixel, and it's a megapixel, so it's a lot of it.
Lots.
It's lots. It's it's supercomputers. The first version. Well, it's a long story where it came from, but So it was that sort of, and this was even before. I mean, I say high dynamic range algorithms now. That's like a standard term. It doesn't sound like a big deal.
Yeah.
But this was 1991. It was before that had been. As far as I know, I invented it. It didn't get picked up or whatever. It was a very specific thing.
So where do you see it going? Are you just going to continue the evolution of this one? Or are you going to create a new species or genus, or what's the future hold?
Well, we're taking it in a couple of different directions. One is, to the high end. So we're going from, what the screensaver version, which is like video resolution. I think 5 years ago I took it to the sort of the high definition resolution, which was great for the gallery. The next step, which is sort of premiering this summer at the Adler Planetarium in Chicago, which is the highest resolution projection system in the world. It's 8,000 by 8,000 projection system. So total, immersive is part of a show there, the premiere. So that's happening. Another direction we're taking it is the opposite way, into the cell phone, into the mobile space. So, which is totally pervasive. Everybody's carrying around a smartphone now and playing with it, and so we want to inhabit that and allow people to interact with the electric sheep, in their pocket, and that's and on tablets too, on the iPad. So those are both. I just had a show in San Francisco. Was it last week to sort of premiere the iPad version, although it's not ready for public sale yet. It's going to take us another month or two to get through the Apple approval process. We have an Android version. It's in your active wallpaper. So and then another direction we're taking, so that's sort of basically, it's doing electric sheep, but in bigger, better, places. Another thing we're going to take it, another direction we're going to take it is to change it in time, which is to make it run in real time. And so a big issue with this has always been, it takes an hour to render every frame, right? So it's really an offline algorithm. It's not. It can't you can't play with it in the way that that it with live music. So I've got in the lab, so it's not really ready to show people, but I've got it working in real time using sort of fewer particles and a different rendering style. And so what that does is the mathematics is the same, and so it keeps the same shapes, and in particular it keeps the same motion. There's something about these equations and the way they move over time, and when you do what I call genetic crossfades, it's very organic. So that's preserved, but it does look like normal computer graphics, and so I'm using OpenGL, sort of standard computer graphics techniques now, taking advantage of the graphics hardware. So you basically use 50,000 or 100,000 particles instead of 1 billion particles, and then it can respond to video camera, it can respond to music, so you can wave your hand, or you can read your face, or it can read the mouse, or you can imagine whatever kind of interactive controls.
Good.
And so those are a couple of things that are either on the verge of release or sort of in the pipeline. And then of course I have speculatively, idea-wise, there's an infinite road that we haven't gone down yet, but beckons.
So how do people find your website?
electricsheep.org for the screensaver download, and scottdraves.com for the limited edition, for the high-end art, and for the sort of the professional presentation.
Can I see your shirt? Lift up your...
Sure. Here's the shirt was another outlet we did as an experiment. We took a still image and printed it with a special printing process, and we made 144 of them, and I put them on the website. I put them on the website and sent email out, and just sold out in 36 hours. So
great. Well, thank you very much, Scott. This is Asheville on June 16th, 2000.